Good morning, good afternoon. How are you today? We are back again with another series for Visual BACnet troubleshooting. Now this time, a little bit more exciting, we are going to go through this live and troubleshoot a couple files that some of our very lucky Visual BACnet users have provided us. These are we've taken a look at these files a little bit ahead of time, as they're a little bit scary. There's a lot of interesting things that we found in this file, and I really hope that going through this session we can shed some light on it and make troubleshooting on some of these problems will make it a lot easier going forward. So I've got Ping here with me as well. So we've got a bit of networking expertise, a little bit of BACnet expertise, and we'll go forward and take a look at this file. So the first one we're going to start with here today is a corporate building. Now this particular corporate building, it's quite a big file. It was taken, the capture was taken for about an hour and a half, and it's got 2.5 million packets inside of it. Why that's relevant is if you were to look at 2.5 million packets inside of Wireshark, that's 2.5 million lines of data. That would be very difficult and lengthy to deal with. In here, put it in here, we've got a poor network health score, 23%, and just looking at the top summary, 8 failed checks and 4 are in warning. So as always, as we go through this information, we want to take a quick look at various things. You can see the traffic rate here. It's hovering on average pretty high, about 750 packets per second as a rate on the entire file, but it's hopping up and down quite severely. So there's obviously some fun in this file. So we're going to dive in a little bit. Normally in these files, we say start at the very top on the critical checks and work your way down the list. Well, in this particular case, there is just a couple unresponsive devices and 1 rejected network. So those, although they're critical, we're going to take a look a little bit deeper down into this score check section, where there's an awful lot more red in it and some more information. We'll come back to the broadcast traffic. In this particular file is very high at 32 packets per second. On average, a well-running BACnet site is about 10 packets per second. So it's running 3 times higher than it should be, but we'll come back to that. When we were diving into this file a little bit more, one of the two key things popped out at us, but one was this global whois router. This is something that should not trigger in a file very often, if at all. And you can see here this 10 or over 1,000 sources of global whois router. So when we click on that,
Ryan, because the file's so big, go to the score at the top. It's just a little faster in this case.
I'm a little bit locked up here.
Yep. So just warning everyone, this, as Ryan said, it's a massive file, 2.5 million packets. Just so you know, we brought it in yesterday into Wireshark just to compare, and a single filter in Wireshark takes about 3 minutes, 2 minutes to run, just a single filter. So if you're going to bring that in, just be aware of that.
So Ping, let's go through this one. So under here, under the global whois router, there are all of these devices that are requesting the global whois router. So they're sending out an overall broadcast, and they're looking for all the routers on the network. All of these devices are doing the same thing.
Yeah, so again, a little background on this. So a whois router is a simple message that's sent out when a device wants to reach another device on a different network. It has to figure out what network it's on, and it just says, who's the router to network 123, whatever. And a global whois router would be saying, hey, every router out there, please tell me which network you are the router to. So if you're in a small system and you have a couple routers, BACnet routers we're talking about here, BACnet routers, it's not a big deal to do a global whois. In this case, we should have shown you earlier, but in the summary, I took a quick peek and it looked like there was over 50 networks, BACnet networks. So there's at least 50 routers here. So you're shouting out saying, hey, every router out there, BACnet router, please tell me that you're there and what network you're the router to. So that's a global whois router. Yeah, Ryan, you want to keep going?
Yeah, absolutely. So in here, we can see that each one of these devices has sent out 4 requests for a global whois router. If you take an average of that out of an hour and a half, they're sending out the request approximately every 20 minutes. But all of these devices are doing the same thing. So let's dig in a little bit deeper and see what that actually means. You can click on any one of these rows, and it opens up another menu down here at the bottom. So
Ryan,
these
can you
are
zoom in a tiny bit? Can you zoom in a little bit just to help everyone follow? Yeah, that's good. That's great.
perfect. So in here, the packets for this source, this is the one that's sending out the information. We can actually click on the row within that expanded menu, and we can go see what it's trying to do. So we can see that each one of these, and this is where we get the time, right? Every time at, looks like 4:43, and then again at 5:13, and then again at, it's very specific. So whatever's happening on this source device, it's doing it at the exact same interval. That's why
And
we
by the
get.
way, what this tells me is that this is not triggered by a human, right? So it's not an operator going out there and say, hey, I'm doing a discovery. I want to find out everything. I'm trying to create a database of some sort. This is programmed in. You can tell it's exactly every 30 minutes. So clearly it's in the programming, these devices every 30 minutes. We can look other ones, but you can see that this is every 30 minutes. So right away it tells you it's not a human operation, right? So sometimes global whois or global whois router, it's used for discovery that we as humans operators want to use. In this case, it's part of the program. Ryan, can you also expand what we call the BVLC, the BACnet Virtual Link Control? So
Yes. Go ahead, King. This is a little bit about BVMDs.
yeah, I was just going to say here, one of the interesting note here is you see under BVLC, BACnet Virtual Link Control, the function it says for the NPDU. So for the NPDU means that this packet was sent through a BBMD. Where you're capturing right now, this customer, this user of ours, captured it at the output of a BBMD. So that's fairly important to note, and that also, if we're on here, you can see the IP address source of the packet at the bottom does not match the IP address at the table at the top. So at the top right now, Ryan is clicking on this 10.200.100.116, but the packet itself. So if you were in Wireshark and you filter by source IP address, the source IP address will be 10.200.254.100. And what this shows is that the .100, 254.100, combined with the fact that the BVLC shows that it's a 40 MPDU, the BBMD address is 10.200.254.100. But the message itself originated from 10.200.100.116, which you can see both at the top in the table and on the bottom at the IP address, just 2 rows down from the point there. So again, this is all information that are available in the packets. You could try to do this in Wireshark, it's just a lot of work. But here in Visual BACnet, that these devices are going through BBMD and requesting a global whois router. So it's shouting out, every router out there, please tell me you are there and which router you're which network you're the router to.
So this probably should be done this exercise should be done maybe once a day or something a little bit less, because it's unlikely that your router is going to change or come online and offline. And it's very unlikely that you're going to keep adding routers to your network. It's kind of like Google Maps creating a bunch of routes. It's already there, and they just choose the one based on your location. So unless something happens and the route needs to change, or we add a brand new road, which is a new route, which doesn't happen as often. So Chris, if you're out there watching the webinar, this is your file. One of the things to take a look at is here's all your source devices on what's happening in the network. and you need to figure out why it's doing this particular exercise.
Yep, and as Ryan showed earlier, there are over 4,000 packets that are shouting out, and the responses. Remember, the responses shout back. They are also broadcast. We can show you that in a moment. But as Ryan said, these should not be necessary. It could be a couple of things. One, it could be just that discovery needs to be turned off or turned down, or it could be a caching problem. I don't know enough about and what product this is, but it could be that the caching table may be limited, and therefore every message that goes out there, it needs to ask. So if you can clean that up, you'll get a much higher performance in.
Absolutely, a much higher performance. Because all these devices that are asking every 20 minutes, right? I mean, the packets go up. There's another way to look at this as well, and that is based on the service choice.
Yep. Yeah, massive file, so give it a moment. We have a fairly optimized database in the back end, but even then, with 2.5 million packets, it does take a while to crunch through it. So while we wait here, who is router? The response will be an IM router 2 or IM router, and both messages typically will be broadcasted. And now you're doing a who is router to all routers global, so this is not directed. So you're not saying who is a router to network 123, and then if you did a directed who is router, again, a who is router to network 123, only the router to network 123 will respond. But in this case, every router will respond with a broadcast message. And again, the other thing to keep in mind here is that all OS-based computing have a limited processing power. So let's take, for example, a Raspberry Pi. If we load a BACnet stack on Raspberry Pi, it could probably handle about 1,000 packets a minute without choking too much. So very often when we say the network is slow, it's not necessarily the network itself that's slow, it's that the devices that are networked are getting so many messages that it cannot process all the messages. And that's why it's so very, very important to turn down as much broadcast as possible to leave room for processing the messages that are meant for that device.
Yeah, and you can imagine a BACnet router. Some of the devices today run a 1 or a 2 gigahertz processor inside of it as a router, not a big deal. But that poor little MSTP device, it's a zone level controller, might only have a 100 or 200 megahertz processor, if that. So there's no way it can handle all that broadcast data.
Let's move on, Ryan. There's a lot of load on the machine yet. Let's move on. Maybe go back to summary, or let me see if I can bring it up. Sorry,
getting all choked out here.
Yeah. Okay, I am here. You want to stick with the corporate building, Brian?
Let's do one more thing in the corporate building.
Sure.
Because there's another thing that we found that we wanted to go through. So under the corporate building, again on the right-hand side, there was this unconfirmed COV traffic. Now, typically unconfirmed COV traffic is very, very minimal at best, but inside of this file, it is showing us at 8 packets per second of unconfirmed COV traffic. That is really, really high. Normally, we almost see nothing inside of this. And this is going to tell us what is actually happening. So this is showing us all of the device, the object type, and the object instance of what the device is and what it's sending. So here's an example of this device, 707.105, an analog input 6, sent 47,000 packets inside of an hour and a half. You can imagine that that is insane. Now, how is it possible that an analog input is sending that much data all the time? Well, once we dig into the packet and click on that row, what we see is the source is sending it to this destination and it's sending the present value. But the present value is 1.008, 1.219, 0.997. Most likely the send interval on the change of value is much too tight and it's sending this way too often. So you can see every second, and it's even higher than that because we only read the value down to the second. So when we're down to the microsecond, it's sending data more often than we're even seeing here. So the same input value is triggering and sending data packets multiple times per second. This is an easy fix. You simply go into the point and you change the COV increment. However, or you change it to polling, or you change it to something a little bit different than what it is. But that's what's causing all of this broadcast issues here, because we're asking, or the COV write issues. So we're asking for the data much too often.
Ryan, do you mind clicking on one of these packets? I'm kind of curious a little bit. Okay, so here's the good news. The good news is that these messages are unicasted. But the bad news, again, is that there are 40,000 packets, whatever Ryan just said. And both machines here, if you think of it from a machine point of view, this machine 10.200.20.5 has to collect the data, create the message, and send it out. And then the other device, the recipient 10.200.254.200, now has to unpack the message, process the message, and then display it or do something with it. So again, the network itself might have lots of room. It might be able to run a gig, but your machines here are consuming a tremendous amount of memory and IO cycles and CPU cycles to create, process this data.
And a lot of this may not be relevant, but here you can see it's actually asking for more than just one piece of data. It's asking for a list of values. So it's asking for who the vendor is. It's asking if it's out of service or not. It's asking for the present value, the reliability, the status flags. So it's asking for a lot of information here within that packet as well.
Yeah, so again, every field has to be processed, right, in the software world at this point.
Good news is for Chris, if you're out there, is this one line, if you can reduce it from almost 47,000 packets down to something a little bit more normal, like the 3,500, you're going to be in a lot better position. But I would also check on these other ones as well, because that's a little bit high.
Yeah. Let's just click on one of the other ones, Ryan. I'm curious also who the recipient is. So in this case, again, this takes a little bit more understanding of the system, but you can see here is a different source, so different device sending it out, but the recipient is the same machine, 10.200.254.200, right? So that machine, again, it already has to process 40,000 packets from this other one, and it still has to process packets from others. So, I mean, unless you're running some massive machine, you're taxing its, again, memory, IO, and CPU.
Perfect. So now that we know what the actual device is, we know what the BACnet device is, we know what the analog input is, and we know what the value is, then it's going to be very easy to go to your front-end software and do some changes, right?
Right. I just want to let you know that we did get a comment from the audience that unfortunately we do see by mistake COV set to 0. Unfortunately, that can cause problems like this.
Okay.
Yeah. Thank you, whoever forwarded that.
Perfect.
And the same person also sent a comment. Usually we get a complaint from the customer, why are my graphics so slow? And there it is. That's exactly what it is. Your
This is
refresh rate is very high, but the machine is not able to keep up with the actual drawing of the graphics. Thank you for
the
that.
normal one. There's also, now that you mentioned that, let's take a poke at the longest response time here.
Yeah.
Because this is where it gets quite fun. So the longest response time, we have a list right here on the top. That's 6 seconds. So when you ask for data, it took 6 seconds to come back to you. And this is machine to machine. This is not me asking my wife to go do something and she's ignoring me and then I get a question. This is machine to machine. And that data should come back sub-second, if not in milliseconds of response times.
That's right.
So
If you look at a network that's MSTP based, having a response time in the 1 second, half a second, even though it might be a little high, it's common. But when we look at an IP network, when something takes 6 seconds, it is not normal at all. I mean, we can through the internet, you can get data from the other side of the world and back within a second, a few hundred milliseconds. So what this says is it's unlikely the problem to be in the network again, right? So it's not a switch that's not keeping up. It's not that your bandwidth is too small. Increasing the performance of your router or your switch will actually probably make the things worse here. It is very likely that either the requesting device or responding device, again at the OS layer, at the software layer, it's taxed so much that it's not able to keep up, and therefore it slows down.
well, let's dig into that. So here we've got a requesting device. This is the 10.200.5160 or device 9998. It is actually asking information from this device, the 254.200. Now, if you recall in the last check that we were doing, that all of that data was being asked by that 254.200 device, which means it's already processing a ton of packets. It's doing a lot of work. And now we're asking it again for more information. And what we're asking it, go ahead, Ping.
No, I just realized the response is abort. So it's not even responding. It's not like 6 seconds later, even though it's slow, it got there, right? It actually didn't even respond. It responded with sorry, I give up.
Yeah, it gave up. It absolutely gave up.
Yeah.
So it just says, okay, it's been here too long. There's no data for you. We're out. So that tells you a lot that whatever device is 254.200 is completely overloaded and things need to be toned down a little bit.
Nice.
But again, here the response time is very consistent all the way through. We've got a lot of things at 600, but it looks like multiple devices are being asked, and that same device at the end is constant in the problem. So between the original problem of the global who is router, between the analog input being requested too much, and this problem, this 10.200.254.200 is the center of all three of those checks.
Yeah. Now keep in mind the problem could be that the problem is not with this device itself, right? It's just that the device is the one that's exhibiting the symptoms, but the problem is likely, in this case, looking at it, it's likely that the whole system is set up with too many global whois router. The COV is going to that machine and it's much too high rate, and everything is asking for information from that machine. So again, not knowing what the system is, if we cleaned up the global whois router and we turned down the COV, I think we would probably see a significant drop in requests, and which would significantly improve the performance of the overall system, but definitely of the 254.200.
I would agree. So Chris, we'll be looking forward to your updates on this as you work through the file.
Hopefully this helped.
Yeah, echoing what Ping started to say, hopefully this helps. We do these periodically every couple months or every 6 months. So if you're stuck, get a file ready and we'll help troubleshoot it. Till next time.
Thank you. Stay home, stay safe.